Hello everyone, I'm Hyunjin Choo from KAIST. Today I'm going to present our work titled on the persistence of higher order interactions in real-world hypergraphs. Let me get started with an introduction. A hypergraph is a generalization of an ordinary graph. As you can see in these figures, while an edge in ordinary graphs joins exactly two nodes, a hyperedge in hypergraphs joins an arbitrary number of nodes. This flexibility allows a hypergraph to represent group interactions among an arbitrary number of entities, such as the sender and the receiver of an email, and the co-authors of a publication. We define a higher order interaction HOI in a hypergraph as the co-appearance of a set of nodes in any hyperedge, and it can be represented simply as a non-singleton subset of nodes. For example, if three co-authors A, B, and C publish a paper together, any combination of them becomes a HOI. A set with Amy, Bob, and Carl in the red box is an example of a HOI. HOIs can appear repeatedly over time. Intuitively, the persistence of those repeated HOIs can be used to measure the strength or robustness of group relations. For example, a HOI with Amy, Bob, and Carl has appeared 3 times over the last 5 years. Moreover, predicting the persistence of HOIs has many potential applications, such as recommending online social network groups and predicting missing recipients of emails. For example, a HOI with Amy, Bob, Carl, and Dan has appeared from January to March, but if Bob does not appear in April, there is a possibility that Bob is omitted. The significance of the persistence of HOIs brings up 3 important questions. How do HOIs in real-world hypergraphs persist over time? What are the key factors governing the persistence? How accurately can we predict the persistence? Let me present our observations in the persistence of HOIs. To answer previous 3 questions, we empirically investigated the persistence of HOIs in real-world hypergraphs from several data domains, including co-authorship and email. We used 13 real-world hypergraphs from 6 data domains. Note that we used the proper discrete time unit for each dataset in this table. Let me first introduce some basic concepts and examples. For each HOIS, we use ES to denote the set of hyperedges containing S, and ES, T to denote the set of hyperedges at time t containing S, assuming each hyperedge EI is associated with the timestamp TI. Then we formally define the persistence of a HOI. Our goal is to measure how steadily a HOI appears over a long period of time, so we consider coarse-grained discrete time units and check whether each HOI appears at least once at each time unit as formalized in this equation. IS, T equals 1 if S is included in any hyperedge at time t. For example, the persistence of S over the interval from 1 to 3 is the sum of IS, T over t from 1 to 3, so the persistence is 2. Let me present what we examined the persistence of HOIs at the hypergraph level. We measured the persistence of each HOI over the first 30 time units after its first appearance. Then we computed the distributions of the persistence of each site, 2, 3, and 4, and fit straight lines on log-log scales. The goodness of fit R squared is 0.9 on average over all 13 datasets. That is, the persistence of HOIs tends to follow a power law. In these figures, the distribution from the DBLP dataset clearly obey power laws. We also examined how the persistence depends on the size of HOIs. To this end, we computed how the average persistence and the exponents of the fitted power law distributions, which are the slopes in the previous plot on log-log scales, change as the size of HOIs grow. Both the average persistence and the exponent decrease as the size of HOI grows, as shown in the relative values in this table. Let me continue to present group-level analysis. First, we examine the relations between the structural group features and the persistence of HOIs, which means the group persistence. To this end, we measure the Pearson correlation coefficient and the normalized mutual information between the persistence and each feature to examine the relation between them. We used 8 group features which are obtained by combining the basic features listed here after a preliminary study. These features include the density and the average size of hyperedges containing S. We divide 2 time intervals for measuring structural features and the persistence. Suppose that a HOIS appears in a hyperedge for the first time at time t. For each HOIS, we compute its structural features from only the hyperedges appearing over the next ts time units after each first appearance. Then we measure its persistence over next TP time units. We fixed TS to 5 and TP to 10 because our findings are insensitive to the values of TS and TP in our preliminary study. Most features are positively correlated with the persistence. On average, the correlation is strongest for the number of hyperedges containing S, followed by the entropy in the size of hyperedges containing S. Our findings are supported by the average mutual information and correlation coefficients in this table. The strongest correlations are shown in detail for 2 datasets in these figures. So far, we used group features to examine the relations between them and the group persistence. Now we examine the relations between the features of individual nodes involved in the HOI and the group persistence. Here we define the 8 structural node features. These node features are computed in the Clique expansions of the hypergraphs. The Clique expansion of a hypergraph is a pairwise graph between nodes, and it is obtained by replacing each hyperedge with the clique with the nodes in the hyperedge. On average, the mutual information is largest for the average degree of neighbors, but they are negatively correlated with the persistence. Our findings are supported by the average mutual information and correlation coefficients in this table. The strongest negative correlations are shown in detail for 2 datasets in these figures. The last part of our observations is node-level analysis. We considered the persistence of HOIs as a group so far. Now we explore the relations between the persistence of each node and the structural features. Here we define a new measure K-node persistence of one node V, which is the average persistence of HOIs of size K is 2, 3, or 4 that the node V is involved in. We use the same node features and measure similarly as in the previous analysis. On average, the correlation coefficient is strongest for the number of occurrences and weighted node degree. Our findings are supported by the average mutual information and correlation coefficients in this table. The strongest correlations are shown in detail for 2 datasets in these figures. From now on, I'm going to present what we assess the predictability of the future persistence of HOIs based on the structural features. We conducted 3 prediction experiments. First, predictability. How accurately can we predict the persistence of HOIs using the structural features? Second, feature importance. Which features are important in predicting the persistence? Third, effect of observation period. How does the period of observation affect the prediction accuracy? We consider 2 prediction problems and formulated them as regression problems. The first problem is persistence prediction. Given a HOIS that appears for the first time at time t and all hyperedges appearing in the past, we predict persistence of S in the near future. The second problem is K-node persistence prediction. Given a node V is involved in a HOI of size K for the first time at time t and all hyperedges appearing in the past, we predict k-node persistence of V in the near future. Specifically, we used past 5 time units to predict the next 10 time units for both problems. For true prediction problems, we used all structural features as input features into 4 regression models. We also considered the mean value of persistence in the training set as baseline and compared it with the regression models. In each hypergraph, we used 2/3 of the HOIs and their persistence and 4/5 of the nodes and their k-node persistence for training and the remaining ones for testing. We evaluate the performance of regression models using two metrics: coefficients of determination R-squared, which measures how well the prediction approximates the real data, and root mean squared error RMSE between predicted and real persistence. Note that a higher R-squared and lower RMSE indicate better performance. All models achieve better performance than the baseline method, especially random forest is most accurate for both tasks. On average, compared to baseline, random forest reduces RMSE by 47% and 28% for problems 1 and 2 respectively. The performance gap between random forest and baseline grows as the size of HOIs increases. For next experiment, we measure the importance of each structural feature in random forest, which consistently performs best. We use the Gini importance to measure the feature importance and compute the rankings based on it. For problem 1, on average, the number of hyperedges containing S and the average degree of neighbors of each node in S are most important among the features. Our findings are supported by the average feature importance rankings in this table. For problem 2, on average, page rank and the average degree of each neighbors are most important among the features. Our findings are supported by the feature importance rankings in this table. Based on the feature importance, we tried reducing the number of input features. We start from using all features and repeat removing one feature with the lowest importance. We can see clear diminishing returns in these figures. That is, the reduction of RMSE due to an additional feature decreases as we have more. Also note that using about half of the features give sufficiently small RMSE. We also investigated how the length of the observation period TS for measuring structural features affects the predictability of the persistence. As shown in this table, when predicting the persistence of HOIs, the average performance gets better and the improvement over baseline grows as the TS increases. However, there is no such tendency when predicting the k-node persistence of nodes. Let me conclude my presentation. In this study, we answered these three questions regarding the persistence of HOIs through hypergraph, group, and node-level analysis in 13 real-world hypergraphs. The questions are: how is the persistence of HOIs distributed? Which structural features govern the persistence of HOIs? How accurately can you forecast the persistence of HOIs? This is end of my presentation. Thank you for listening, and if you have any question, feel free to ask.